Okay, this is the second video lecture for Math 181, Calculus 1. This is the video lecture for Monday, April 6th. Okay, again, the idea with these video lectures is for you guys to watch the video lecture before class time. Then we come together at class time and we have an opportunity to have a class discussion where you guys can ask me questions about the material. We can do additional practice problems. Or we could do homework problems for the assignment that was due that day. Okay, the topic for today, we're actually going to talk about two important theorems relating to derivatives. And the first theorem is called Rolle's theorem. Let me find a different pen. This pen looks a little bit dry to me. Okay, what Rolle's theorem says is if, and there's three conditions of this. If you have some function f, which is continuous, so f is continuous on the closed interval ab, and f is differentiable, so we have some function f. It must be continuous on the closed interval AB, differentiable on the open interval AB. So imagine we have some interval. We have some function, we have some interval, and we're interested in talking about this function on that interval. And the third condition of Rolle's theorem says that the value of the function at the endpoints is equal, and if f of a equals f of b. That means the value of the function is the same at the endpoints of this interval. What this means is then there exists some number c such that f prime of c equals 0. So then there exists some number c such that the derivative of the function, and this c, by the way, this c is in, such that c is in, I forgot to mention that, in the interval AB. So there exists some number c in the interval AB, basically a value of c between a and b, such that f prime of c equals 0, such that the derivative of the function at this number c between a and b, there's at least some number c such that the derivative equals 0. Okay, this might seem a little bit sort of high-level math jargon here, but actually this theorem makes quite a lot of reasonable sense. We're not going to prove this theorem, but we're going to justify the reasonableness of this theorem. And basically in words, what this theorem says is if you have some function that has the same value at two different points, then there must be some point in between those 2 points where that function either maximizes or minimizes. Because remember, if you have a derivative equal to 0, that usually means you have a maximum or a minimum. So what this is saying is if a function has the same value at 2 different points, there's a point in between those 2 points where the function is maximizing or minimizing. Let's represent this graphically. So for instance, let's say I draw some function, and I don't know what the equation of this function is, but we can draw some function. Let's say it goes like this. And there's 2 points. Let's say we have an interval. Okay, we have an interval a and b. Okay, and this is f of a, and this is f of b, right? And these values, these have the same value. The function has the same value at a and b. Then there must be some point c, right? And c would be this point. There must be some point c where f prime of c equals 0. In other words, where the derivative of the function at that point c equals 0. In other words, where we have a slope of 0. In other words, where we have a maximum or minimum. Or we could have some other function. It might look like this. Okay, we have a point a and b. Okay, and again, if we have a point a and b where our value of our function, this is f of a, this is f of b, where the value of the function is the same at these 2 points, and there must be some point c, it looks like it's about right there. There must be some point c where f prime of c equals 0. So this theorem, I'm not going to prove it, but it actually makes, if you think about it, it really makes a lot of sense. In fact, we could have more than one maximum or minimum. Let's draw a function like that. So we don't need to just have one maximum or minimum. We could even have a function that looks like this. Like that. Okay, and let's pick a couple of points A and B. We need to pick these A's and B's such that the value of the function is the same. So this is f of A. This is f of B, right? The value of f of A equals f of B. The value of f of A and f of B, these values are equal. Well, there are some points C. There's actually 2 points C here, 2 points where the slope of the function is 0 between points A and B. So we have one point, we'll call it C1. So here, f prime of C1 equals 0. There's another point here, C2, and f prime of C2 equals 0. So in this case, there were 2 points between A and B where the slope was 0. There could be 3 or more points. There could be 3 points or more points. But there has to be at least 1 point between A and B if those conditions are met. If f is continuous between A and B, if it's differentiable between A and B, and if f of A equals f of B. Okay, basically if it's a well-behaved function. Okay, let's do an example problem involving Rolle's theorem. Just slid around a bit there. Okay, so here's an example problem we can consider. Let's suppose we're given some function f of x equals 2x squared minus 4x plus 5. Okay, and there's 2 parts to this. Let's first verify the conditions of Rolle's theorem. Let's verify the conditions of Rolle's theorem. If you guys remember, the 3 conditions are that this function is continuous. Oh, I need to give you guys the interval too. I am sorry. The interval we're interested in is minus 1 and 3. I'm sorry about that. This is the interval we're interested in. Let's verify the conditions of Rolle's theorem. The first condition is that the function be continuous on this interval. Well, this is a polynomial, okay? And as we learned, polynomials are always continuous everywhere. So the continuity is taken care of. So continuity, you can check that off. Differentiability, check that off as well. Any polynomial is differentiable everywhere. So we know that the function is continuous and differentiable on this interval and really anywhere, any value of x. The third condition is that the function have the same value at the endpoints of this interval. So the question is, well, let's calculate f of minus 1. Okay, f of minus 1. If we plug in minus 1 here, we get 2 times 1 minus 4 times minus 1 plus 5. Let's see what that comes out to. We get 2. This is 2 minuses make a plus, so we get plus 4 plus 5. Okay, this equals 11. And then what we can do is plug in f of 3. Okay, if we plug in f of 3, we get 2 times 3 squared minus 4 times 3 plus 5. Let's see what that equals. This is 9, this is 18, right? Minus 12 plus 5. And this equals 11 as well. So we've just verified that the value of the function at the 2 endpoints of this interval is the same. So we've verified the 3 conditions of Rolle's theorem. And the second part of this example is let's find the value of c on this interval AB such that f prime of c equals 0. So we're going to find all c's such that f prime of c equals 0. And these c's will be only on this interval here. How do we do this? Well, basically, we take the derivative of our function with respect to x. So we take the f dx. Okay, and let's do that. This is a simple polynomial, so we get 4x. Okay, we get 4x minus 4. And the condition is that we're trying to find the values of c such that the derivative equals 0. So we set this equal to 0. And now we solve for x. We get 4x equals 4, which means that x equals 1. So c, in this case, c equals 1. So this function has a certain value here. So the value of c equals 1, which is on this interval, right, is the value at which this function has a zero slope. Okay, this is Rolle's theorem. Let me graph this function in Desmos, and I think this will make sense to you guys what's going on here. Okay, let's go to Desmos here, and I'll show you guys this in a second. I'm going to graph this function, 2x squared minus 4x plus 5. Okay, we'll zoom in here. Okay. Now I'm going to show you guys this on the camera. Okay, so if we're looking at this function here, our interval was -1 to 3. Here's x equals -1. Here's x equals -1. This is x equals 3. And we can see that the value of the function at these 2 points is equal to 11. So we have equal values of the function at these 2 points of -1 and 3. And then what we found a point in between -1 and 3. It happens to be x equals 1, where our slope is 0. In other words, we had a minimum here. Our slope is 0. So this is a great case of using Rolle's theorem. We first verified the conditions of Rolle's theorem were true, and then given those conditions, we used Rolle's theorem to find the point at which the derivative was 0 between these 2 points. Okay, I'm going to put the camera back. And we're going to talk about a second theorem. We're going to talk about a second theorem called the mean value theorem. Again, I'm not going to prove the mean value theorem, but we will justify it and talk about how it makes sense. The mean value theorem is actually very similar to Rolle's theorem. So there are actually 2 conditions for the mean value theorem. And one of the conditions is that f is continuous on the interval, on closed interval AB. So again, imagine we have some function and we're interested in learning about this function on a certain interval AB. F is continuous on the closed interval AB. And if f is differentiable, on the open interval AB. Okay. Then there exists some c in the open interval AB such that f prime of c equals f of b minus f of a over b minus a. Or we could rewrite this. We could rewrite this as, if we do a little algebraic manipulation, we could rewrite this as f of b minus f of a equals f prime of c times b minus a. Okay. So this is the mean value theorem. Again, we're not going to prove this, but we'll talk about the reasonableness of it. Okay, what this is really saying is if you have some function that's well behaved on an interval AB, in other words, it's continuous in that interval and it's differentiable in that interval, then there has to exist some point in between A and B such that the slope at that point is equal to the slope of the secant line, is equal to the slope of the secant line connecting points A and B. So if you have two different points along a curve, if you have a curve that goes from point A to point B, okay, then there has to exist some point C between A and B on that curve where the slope of that, where the slope at that point C is equal to the slope of the secant line connecting points A and B. Again, this might sound a little bit confusing, but what we can do is create a graph. What I want to do is create a graph of these types of functions. And let's actually verify this is true. I challenge you guys to come up with any function, give you guys an A for the semester. If you can find any well-behaved polynomial function and have some interval a, b where there's not some point C between A and B that has the same slope as the secant line connecting A and B. You can't do it. So you have to have at least one point where you have the same slope. And what we can do is create a graph of this. And let's pick just some random function. Let's pick a function that goes like this, goes down like that. We're going to pick 2 points A and B. Now the difference here between the mean value theorem and Rolle's theorem is, if you recall with Rolle's theorem, we have to have the value of the function at our two endpoints has to be equal. That's not true. That's not a condition of the mean value theorem. So we can have different values of our function at different endpoints. This is point A. This is point B. This is f of A. This is f of B. And what I'm going to do is use another pen to create, what I can do is draw a secant line. Not exactly straight, but it should have been straight. I can draw a secant line that connects points A and B. Okay. I just got an email. I'm actually monitoring a test here. Okay, so we're good. Okay, and the slope, if you wanted to find the slope of the secant line, AB, is equal to, if you guys remember, it's f of b, the second y value minus the first y value, it's our simple slope formula, over b minus a, over the second value of x minus the first value of x. This is the slope of our secant line. Well, if you look here, there has to be a point, and it looks like the point is about right here. There has to be a point C. Okay, there has to be a point C, such that, and let's draw the slope of the tangent line to this point, which is, by the way, the derivative. There has to be some point C such that f prime, I'll put my marker back sheet. There has to be some point C such that f prime of C equals MAB. There has to be some point between A and B such that the slope of the curve at that point is the same as the slope of the secant line connecting points A and B. Okay? We could have a case where we have 2 points. We could have another curve. We could have a case where we have 2 points, A and B, not necessarily the same value of the function at those points, right, A and B. And if we were to draw the secant line here, the secant line is this line. That's our secant line. And actually, in this case, can you guys see that there's actually two points along this curve? There's 2 points along this curve where the slope is equal to the slope of the secant line. And it looks like one of those points would be about right here. So this would be C1. Then a second point would be about right here. This would be C2. And then the slope of the, if we draw this is a little bit difficult to draw, but you guys get the idea. There's actually 2 points along this curve between A and B where the slope of our function at those 2 points is equal to the slope of the tangent line connecting points A and B. So this is a graphical illustration of the mean value theorem. And what we're going to do now is do one more example problem involving the mean value theorem. So let's consider the function, so here's an example problem. I believe this is example problem 2. Let's consider the function f of x equals 2x squared minus 3x plus 1. And let's suppose we're considering the interval 0, 2. Okay. And first thing we want to do, part A, is we want to verify the condition of the mean value theorem. Let's verify the conditions of the mean value theorem. Actually, the conditions are pretty simple. This has to be continuous in this interval. Since this is a polynomial, it will be continuous on this interval. This has to be differentiable on this interval. Since this is a polynomial, it's differentiable everywhere. So this polynomial will satisfy, or any polynomial will satisfy the conditions of the mean value theorem. What we want to do in part B is we want to find the values of C on this interval AB such that that the slope of our function at those points is equal to the slope of the secant line connecting these 2 points. Well, we first need to find the slope of the secant line that connects these 2 points. And the way we do this is we plug in 0 for x. So f of 0, let's plug in 0, equals 1, right? If we plug in 0 for x, these 2 terms go away, we get 1. Let's plug in f of 2. Okay, so we get 2 times 2 squared minus 3 times 2 plus 1. This equals, looks like 4, 8 minus 6 plus 1, which equals 3, right? So f of 2 equals 3. Now we can calculate the slope of the secant line, AB. The slope of the secant line will be f of 2 minus f of 0 over the point 2 minus 0. This equals 3 minus 1 over 2, which equals 1. So that is the slope of the secant line connecting points 0, x equals 0 and x equals 2 for this function is equal to 1. Okay, and now what we want to do is we want to find the value of C. Find the value of C such that f prime of C equals the slope of the secant line, which is 1. So let's find those points. What we do here is we take the derivative of this function again. We do the f dx. Take the f dx of this function, okay, which is going to be 4, take the derivative of a polynomial, is 4x minus 3. But now we want to find the points such that the slope of our function equals 1, equals the slope of the secant line. So now we'll plug in, we want to force this slope to equal 1. Okay? And then we solve for x. This means we get 4x equals 1 plus 3 equals 4, which means that x equals 1. So that means that C, should have said C equals 1. So there is a point on this interval, there has to be a point by the mean value theorem, on the interval 0, 2 for this function, which has a slope equal to the slope of the secant line connecting these 2 points. And it turns out that point occurs at x equals 1. What we can do is, again, we can go to Desmos here, and we can use Desmos to verify this graphically. Let me just log into my computer. Okay, let's go to Desmos, and I'll show you guys this in a second. I'm going to graph our function here. So this is a graph of our function. Let me show you guys that. This is our function here. The interval we were interested in was the interval from 0 to 2, okay, to that point right there, 0 to 2. And note here that the value of the function was not the same at our 2 endpoints. So this is not a case of Rolle's theorem, but it is a case of the mean value theorem. If we connected a point from this point, if we connected the 2 points of our interval together, we get a secant line that looks like that, if you can see that little marker on there. would look like this, okay? And then what we found is there's some point along this curve. It happens to occur at x equals 1, where if you drew where the slope of the curve, or the slope of the tangent line to this point right here, has the same slope as the secant line connecting these two endpoints. We found that point. That point is x equals 1. And looking at this graph, that makes sense. It looks like at approximately x equals 1, actually exactly at it, if you were to draw a tangent line to the curve at that point, it would have the same slope as a line connecting the two endpoints, as a secant line connecting the two endpoints. So that's the idea of the mean value theorem. Okay, well, that concludes our lecture. We talked about the mean value theorem. We talked about the Rolle's theorem, and we did a couple simple examples with that. So at this point, I'll end the video, and I will see you guys on Monday, April 6th at 8 a.m. All right.